All right, so now that we can handle our forces and our vectors, we can do the math, right? We can break forces into their components. Now we can add them up to zero. So let's look at chapter 3, equilibrium of a particle. Now we know Newton's first law, that an object at rest stays at rest, an object in motion stays in motion. We're in this class, statics, we're going to be looking at objects that are kind of staying at rest. It just means that the sum of the forces is equal to zero. So this is statics, right? In statics, acceleration is zero, so the sum of the forces equals zero. This is actually a vector, the sum of the forces vector. I like to separate these and sum up all the forces in the x direction equals zero. Sum up all the forces in the y direction equals zero. And if we have 3D, sum up all the forces in the z direction equals zero. Okay, so I want to sum up all the forces acting, so I need to draw all the forces acting. I need to know all the forces acting on an object, and that's our free body diagram, a diagram showing all the forces acting on an object. So here's my 1, 2, 3 steps. Draw the point, or maybe if it's a box, draw a box. If it's a wheel, draw a little wheel. Draw, and right now we're looking at particles. So just draw the object, draw the point, and then label the axes. Draw and label the axes. That is one of the most important parts of this problem, is defining your axes, so that when you start summing the forces in the x, you know what the x direction is. You know which direction is positive, and you can define your axes however you want to. Do you want x to be positive to the right or positive to the left? Do you want y to be positive up or positive? You can define your axes. If you're on an incline, you don't have to define your axes perfectly horizontal and vertical. You could define x, up the incline. You can define your axes. Just stay consistent. Stay consistent. All right, and then draw and label all forces. Draw and label all forces. And I want you to do number 4. Label all angles, dimensions. Here we go. I want you to make your free body diagram. Make your free body diagram self-sufficient. Self-sufficient. Meaning all of the information in the problem statement should be in your free body diagram. You shouldn't have to go look at your free body diagram and then go back and look at the problem statement. You should be able to just look at that free body diagram and know all the forces, all the angles. Make it self-sufficient. Put all relevant information in your free body diagram. All right, so what are some of the forces we will see in our free body diagram? I think you've done this in physics, but I don't want to leave anybody behind. Let's talk about some of these. Let's start with the weight, because I always forget the weight. If you have something that has weight, then you have the force of gravity, or the force of the weight, always pointing straight down. Always pointing straight down, right? The weight is equal to mass times gravity. So be careful. Did they give you the weight, in newtons, or did they give you the mass in kilograms? And of course, gravity would be in meters per second squared. Gravity is 9.81 meters per second squared. I like 9.81 meters per second squared, not 9.8, and definitely not 10. Let's do 9.81 meters per second squared. But we sometimes will have English units, and in English units, pound, it is pound force. That is the weight, not the mass. So generally, when we do problems in this class, if I tell you something is 100 pounds, that's its weight. That it's 100-pound force. Okay, so if you have something that has, mass, that has weight, put the weight acting straight down from the center of the point. Okay, we'll see a lot of ropes and cables. All right, we'll see a lot of ropes and cables. Ropes are always in tension, right? Ropes can only pull. Ropes can't push. So ropes are always in tension. Ropes are always pulling. So that force needs to be pulling on your point. Okay? We can assume, it's a good assumption in this class, that the tension in a rope is constant throughout the rope and constant around a pulley. So for instance, if you've got some rope that is wrapped over a pulley, then, if we're looking at this block, this object, the tension in that rope is going to be the same as the tension in acting on that object. All right? So tension in a rope is constant throughout the rope, whether you're on this side or this side or this side, and it stays the same, or even though it goes around a pulley. And they have negligible weight. The actual rope has negligible weight, so you don't have to worry about the weight of the rope. You just have to worry about the force of tension in the rope. Okay, and then let's talk about normal forces. This is maybe the hardest one, the one where we'll have the most trouble. A normal force is a force of one object pushing on another object. Generally, it's the ground pushing on your object. If you've got something sitting on the ground is pushing up on your object. You might draw it down here, but I was taught, and I draw it kind of up here, but it is the ground pushing up on that object. Now, it's not always up. It is always perpendicular to the surface. So if you've got a block that's on this 30-degree ramp, this 30-degree incline, your normal force would be perpendicular to that 30-degree incline. Now, this is how I like to do it. You could kind of draw some triangles and figure out if this is 30 degrees, this is 30 degrees, this is 60, this is 30. This is how I like to think about it. If my incline is 30 degrees from horizontal, and I want something perpendicular to the incline, then my force is going to be 30 degrees from vertical. Things that are perpendicular, you kind of switch the x and y. You kind of flip the horizontal and vertical. So the incline is 30 degrees from horizontal. My normal force is 30 degrees from vertical. Sometimes instead of giving you an angle, they might give you some dimensions like a 3, 4, 5 angle. First of all, a 3, 4, 5 is not a 30-degree angle. Let me reiterate, the 3, 4, 5 is not a 30-degree angle. We could do tangent to figure out what it is. But if we're given the dimensions of the incline and the normal force right here is perpendicular to the incline, then this is how I like to think about it. I'm kind of going to switch the x and y, switch the horizontal and vertical. So this is going to be at a 4, 3, 5 angle. Okay? Okay, so normal force is when one object is touching another object, generally the ground, touching your object. Don't throw in normal forces when there are nothing touching, when things aren't touching. Don't put in a normal force if there's not actually the ground or something touching your object. And that normal force is always perpendicular to the surface it is touching. Okay, the force in a spring. The force in a spring, I don't know how you did this in physics. Force in a spring is K delta X. K is the spring constant. So here we go. K is the spring constant. It's just how tough, how hard that spring is. And delta X is the amount of stretch or compression, amount of stretch or compression of the spring compared to its unstretched length. the amount of stretch or compression of the spring compared to its unstretched length. That delta x is not the length of the spring, right? That delta x is not the length of the spring. That delta x is the stretch of the spring. Okay, that delta x is the stretch or compression of the spring. Now, in physics, I think we might have been taught that this F is negative K delta X just because generally a stretch gives you a force in the opposite direction, so that negative is just kind of about the direction of the force. Since it's about the direction, and since I'm drawing the forces my own directions, I don't worry about pluses and minuses. I just think to myself, is it being stretched? You know, is this spring being stretched from its unstretched length? If the spring is being stretched, then it is in tension, right? It is pulling, right? Remember, tension is always pulling like a rope. It is always pulling like a rope. If it is compressed, then it is in compression. It would be pushing on my object. It would be pushing on my object. So I don't have a negative there because I'm drawing it the correct direction to begin with on my free body diagram. Okay? All right, so those are not complete, but those are the forces that we'll be looking at for these free body diagrams for these 2D problems. Before we get to some problems, let's look at a few free body diagram, a few things we'll tackle in our free body diagrams. Okay, first of all, you might have a lot of objects, all right? Then you can have a lot of different free body diagrams. You could have the free body diagram for D. Let's draw box D right here. So this is how I would do it. I would draw D right here. I would draw the weight of D and then the tension right here. Let me call this tension 1 because I see a few ropes, I think some different ropes, so the tension is the same throughout a rope, but if it's a completely different rope, then a completely different tension. Okay, and then I could sum the forces in the y direction. I didn't define my axes. Let me define my axes. I think I'm going to say x, y right here. I could sum my forces in the y direction. So T1 minus WD equals 0. T1 equals WD. This is in statics, not in your other classes, not in dynamics, but in statics for a block that is hanging by a rope. All right, in statics for a block that is hanging by a rope and no other ropes, no other forces here, the tension is equal to the weight. All right, in statics, if it's hanging straight down right here, the tension in that cable is equal to the weight. Okay? For instance, also, let's look at E down here. Let's look at E right here. I've got the weight of E, and then I've got this tension in here. I could say T2 or something, right? But can you see that this is going to be equal to the weight of E because we're in statics, and it comes back to summing the forces equals 0. All right. So that when we get to A, so I can draw a free body diagram of this ring A. See how you can draw different free body diagrams. Draw the free body diagram of this. Okay, so this rope right here is tension 2, the same as that tension, because it's the same rope. But do you see that I drew it pulling on A? Tensions are always pulling on A. And it is, I already found, was equal to the weight of E. Equal to the weight of E. This tension is T1. It is at a 4, okay, and I don't have this dimension S, but it's at a 4 by S, angle right here. And then I've got this other tension, we'll call it tension 3 right here, that is at a 4 by S angle. This tension, can you look ahead? It is going to be the weight of F. this tension is the same as that, is also going to be the weight of D. So you can take some shortcuts. I probably didn't have to draw the free body diagram for E, for D, and for F. I could have kind of just started with A, knowing I've got the weight of F right here. I've got the weight of D right here. I've got the weight of E right here. But you can draw, and sometimes you might need to draw free body diagrams of different objects separately. And then sum the forces. So here's the heart of my problem. And I would sum the forces in x equals 0, sum the forces in y equals 0. All right, how about this? We've got a chandelier hanging by two springs. I would draw a free body diagram of this right here. Let me draw this free body diagram. I've got the weight of the chandelier. I've got the force in this spring and the force in this spring. All right, if I'm at that angle, let's look. Let's define this angle on my free body diagram. If I'm at that angle, then this would be theta. That angle, this would be theta. And the force in a spring is K delta X. Delta X is not the length of the spring, but I probably am going to need to figure out or find, or maybe it'll tell me, I'm going to need to figure out that length of the spring and subtract the unstretched length. For example, if I don't know, for some reason, I found that the length of the spring was 6, and it told me that the unstretched length was 5 feet, then my delta X would be 1 foot, right? K delta X is the stretch of the spring. Do you see that I drew it in tension? So I'm assuming that it is being stretched. And so if I'm told that its current length is 6 and its unstretched length was 5, yeah, it's being stretched. If for some reason I know that its length is 6 and maybe it's, you wouldn't ever have compression in this scenario, but sometimes you could have compression of a spring. If you have compression of a spring, you would need to draw it pushing on my object. But this is obviously a spring that is being stretched, so it is pulling just like a rope on my object. All right, and then we'd need a lot more information, but then I'd sum the forces. Let me define my axes, x and y. I'd sum my forces in the x direction, sum my forces in the y direction. All right, let's look at this real briefly. I don't think I'm going to draw the free body diagram of B, because the only thing that it would tell me is that, hey, the tension in that rope is the weight of B. So I don't think I'm going to draw that. But I am going to draw the free body diagram for A. So I've got A right here. Before I forget, I've got the weight of A. And here I've got the tension, which is the weight of B. So maybe they tell me the weight of B. Maybe they tell me the mass of B, and then I'd take M times G to find the weight right there. So this is at a 60-degree angle. Let me define my axes. All right, so I need the normal force, right? Because this is touching the ground. So I need to draw the normal force right here. What angle is it at? Well, it is perpendicular to the incline. So if it told me this was 60 degrees, it would be 60 degrees right here. If it told me this was, a 5 by 12, then this would be a 12 by 5. It is perpendicular to the surface. Most times it'll tell you the angle right here, and you can figure out what's perpendicular to it. This one is a little bit more interesting. It gives us an equation for that incline. All right, it gives me an equation for that incline. And so I would need to know the slope. What is the slope of this incline? How can we find the slope of this equation? The slope of this equation would be the derivative. right? The slope would be 5x. So at x is equal to 0.4, this slope is 2. All right. So if this slope is 2, slope is rise over run, then the slope of this would be 1 over 2, right? Remember, just mathematically, calculus or wherever, two lines that are perpendicular to each other, the slope is the negative reciprocal. All right, negative is just the direction, but so the slope is the reciprocal. So this is if this is a rise 2 over 1, this is a run 2 rise 1. Run 2 rise 1. Okay, that was the hardest. Generally, if you've got something on an incline, if it's a 40-degree incline from horizontal, then the normal force is going to be 40 degrees from vertical. All right, then I would sum the forces in x equals 0, sum the forces in y equals 0. All right, now I think we're ready to put this into practice.